Hi, this is Ray Salemi, and along with Tom Fitzpatrick, I'm presenting my Python implementation of the UVM. So this is based on the idea that when you look at a test bench, there's test bench software that creates stimulus and checks results. It talks through a proxy of, say, function calls to drive the stimulus into the DUT and read the results back. And we currently write that software in System Verilog, but we could write that software in Python. So you might ask, how do you connect Python to a simulator? Well, Python connects to C, and simulators connect to C in many ways. There's the VPI and the VHPI and the DPI. In this case, we're going to use an open source project called CocoaTB that will connect to the simulator through the VAPI and the VHPI, and we're going to use it to create the proxy with its functions, and then we're going to use it to create drivers and monitors. So let's look a quick look at why we would want to do this in Python. The biggest reason is there's no typing in Python, and so it becomes much easier to put the UVM together. You don't have a situation on the right where you have to use parameters when you create the FIFOs, and then if you put the wrong thing in the FIFO, then you are in trouble. Instead, in Python, instead of moving data around, which requires data widths to match, we simply move handles to objects around. Everything is an object, including constants. So we see here AA points to a constant, that's an integer 6,000. BB points to a constant, that's a floating point 1,600. When we say AA equals BB, all we do is copy the handle, and the 6,000 eventually gets picked up by garbage collection. Now what happens if you get the wrong thing? So in System Verilog, we see we have a get port there that's of type duck, and we have a variable integer, and we try to get the duck and put it in the integer, and we get a syntax error. In Python, we have a similar problem. We have a port that should have a duck, but we put an integer into it. We get the II variable out of that port, and we try to make it migrate. And when it goes to migrate, it raises an exception. It says, I don't have a migrate in an integer. And that's how Python works. You don't ask permission to use a variable. You use the variable, and if it works, it works. And if it doesn't work, you debug. And it turns out this is a very efficient way to create software and to create a test bench. So let's look at the pyuvm. Pyuvm is installed and available on PyPy. It's you say pip install pyuvm, and you'll get it. And then when you're in your code, you say from pyuvm import star, and that imports all of the labels from the pyuvm, and you get real UVM behavior, like this ALU test that has a run phase, that raises objections, it gets a sequencer out of the config.db, it creates a sequence, it launches the sequence, it waits for it to finish, and then it drops its objection. Right there we have the UVM, but written in Python. If we look a little more closely at an ALU agent, we see some elements of Python with UVM. First thing, I've saved all the names from the spec. So UVM agent is UVM underscore agent the way it is in System Verilog, not camel case like normally in Python. We don't have macros. So everything that extends UVM void is in the factory, is registered. There's no phase arguments because I refactored the phasing system to be just the common phases. We'll talk about that later. You'll see it's easier to access the factory. There's no : type ID : create. It's just class name dot create. The config.db is the same way. There's no there's no typing involved, and so there's none of that hashtag and the type that goes in the config.db. There's just one config.db that stores everything. If we don't find the thing we're looking for, it throws an exception, and we can manage that, or we can let it rise up and stop our program as a UVM fatal would. And introspection allows us to do things like pass the name of a function to a class when we create it, and it'll use the string name of the function to find the function that it should be running. And this makes it easier to reuse code. If you go through the spec, there are nice chapters where everything is, and these are the chapters that have been implemented, or mostly implemented. There are some things that are not in here, like transaction timing and other elements that relate to working in a simulator. And also there's been some simplification. As you can see, phasing has been simplified and refactored. sequences in the sequencer have been simplified and refactored. But all of these things have at least been implemented, and these are what go into your typical test bench. Here are the ignored UVM features, things that were too complicated to implement, like the custom phasing, really not necessary because Python has ways of handling container classes and synchronization. Of note, the report handlers are replaced by logging, as we'll see later, and someone one day will probably write the register layer as an open source project. So why don't our classes need to be registered with the factory? How are they automatically registered? That's implemented in Python using meta classes. So meta classes are used to initialize a class object. When you say class, say ALU test, it creates an object called ALU test of type class. And that object needs to be initialized. The init function initializes objects, and we normally call the type version of the init function to initialize an object. But we can extend type, override init, and do other things when we create a new class. So in this case, we created factory meta, and factory meta stores the class in an associative array indexed by the name of the class, which you can see how that makes it easy in the future to do overrides and whatnot. Then we declare UVM void to be meta class of factory meta, and now everything that is a UVM void is automatically in this associative array that contains all the classes. UVM factory is a singleton, and we have another meta class that handles the singleton functionality. So whenever you create a UVM factory, you either get the first instance that was created, or in the future, the same call gives you the other instances. There's no need for that : get that we normally use for singletons. And you can see here the UVM factory, we're getting this singleton and calling set type override by type. So now you can use the factory very cleanly. You don't have to go through this Herculean driver : type ID : create . You just say driver.create, and you have the factory working the same here as it does in System Verilog. The config DB is also the same way. It's a singleton, so you say config.db.set, and the functionality is the same. So you pass it none. None is the same almost as null in System Verilog. In System Verilog, null is a non-pointer. In Python, none is an actual object called none that is a singleton across the whole program. So you say set none, and then you have the same star, and then the label, and then the handle to the thing that you're storing in the config DB. When you get it out, you get it out the same way. You pass out a handle to yourself, which is similar to this in System Verilog. It doesn't have to be called self, whereas System Verilog is a keyword this. And in this case, we're getting the sequencer out. If there is no sequencer, it'll raise that exception that we saw earlier, and in this case, we probably let that go to the top and stop the program, since that's essentially a fatal error, as we see in the System Verilog code. Threads in Python are different than processes in System Verilog in that you just can't kill a thread, whereas System Verilog just shuts all the processes down when it's done running. You have to write threads in Python so that they can be notified that it's time to die, and then they gracefully exit themselves. In this case, we're doing this with a UVM queue, which is built on top of the Python queue, which is its coordinating inter-thread communication class. And what you do is, in this case, we extended the UVM queue to modify the get function. And the way the get function works in a UVM queue is that you call get, which is blocking, and it goes into a loop. And the loop at the bottom there, the while loop, says while not self and while predicate. That predicate that we're waiting on is a function call that we set up above, and it's called run phase complete. So what we're saying is, while the run phase is not complete, do this loop. And what it does is it goes through the loop, it calls get, it blocks, but it blocks with a timeout. If the timeout triggers, it raises the queue.empty exception. So we jump to the except line, and the pass is a no-op. So we go back to the top of the loop. And we keep doing that until either run phase is complete, in which case we exit, or until we get data, and then we return it and we exit until the next time we're called. This allows us to create TLM FIFOs. TLM FIFOs in the pyuvm are like the ones in System Verilog UVM. They have exports, non-blocking exports. In this example, is a non-blocking get export. And we can see that in the TLM FIFO, we have used multiple inheritance to create our non-blocking get export. It is both a thing called a queue accessor, which is an object that can access a queue, and by the way, also an analysis port. Also, it's a UVM non-blocking get export. So that is used elsewhere in error checking to make sure that the ports and the exports are connected properly. And we see here that given a queue, we store the queue in self.queue and the analysis port and self.analysis port. We also call the initialization function for UVM component and pass it the name and the parent so that we're in the hierarchy as we're supposed to be. And you can see now we implement, say, can get is simply return not self.queue.empty. Try get, we do a self.queue get no wait, which if the queue is empty, triggers a queue empty exception. And you can see here in Python, we can return more than one object on a line. So if we get our item, we return true and item, and that means it was successful. Otherwise, we return false and none, and that means that it was unsuccessful. Phasing has been simplified and refactored rather than have the complicated system that allows you to create custom phasing that's rarely used. The UVM spec specifies common phases, which are the ones we all know, and so those have been implemented here as classes, either top-down phases or bottom-up phases. They're differentiated by what their traverse method does. And here you can see the UVM build phase has been declared as a top-down phase and a common phase. And then the common phases are all stored in a list, and that list gets run through in the run test function to run through the hierarchy and run the phases on all of the objects there. Sequences have been refactored in the spec. There are 2 chapters on sequencers and sequences. They're very long, they're very complicated, they sort of interlock, and they probably, when you write everything, if you write it perfectly, in the end it all works. On the other hand, if you just know what sequences and sequencers are supposed to do, you can just implement that in Python, and that's what I did. I just implemented it from scratch to get the same functionality. The only simplification is I only wrote the FIFO arbitration for having multiple sequence items in a sequencer, but it could be a project in the future to add the other kinds of arbitration. pyuvm doesn't use the UVM logging system, the UVM reporting system that comes from the UVM. It leverages the logging system that is already shipping with Python in the logging module. There are some differences between Python logging and UVM logging. There are no message IDs, and you can't control output based on message ID. There is the equivalent of verbosity, it's called levels, and the nice thing about Python logging levels is that they're consistent, in that in a System Verilog UVM you had to set you set the verbosity level for a component, say, and then messages that were below that verbosity level could go under that ceiling and be printed. So you had this weird thing where you gave them lower numbers to make them more likely to print. In Python, the higher numbers are more likely to print, and the logging level presents a barrier that a message has to get over by having a high enough level. Handlers let you send your data to different places. By default, it goes to the screen, but you can add handlers to go to files or HTML, or there are a variety of handlers available out there. And formatters format the message for a given handler. We see here, by the way, that pyuvm has an additional logging level called FIFO debug. If you lower your logging level to that number, 5, to FIFO debug, you'll see messages from the FIFOs showing what's being written and where blocking has happened that you can use for debug to see why your test bench might be locked up. You use logging by using the self.logger member that's in every component, and you can see here it's self.logger.debug.info.warning to output the messages. And the formatter tries to make it look like system verilog report, log messages, except between the square brackets, that's not the message ID. That's the spot in the hierarchy where the message is coming from. We can control logging by setting the logging level, and we can do that on an individual object or hierarchically throughout the hierarchy of components. We can add a handler to given again to a single component or hierarchically, and we can set the formatter on all the handlers that have been added to a given object so that they all have consistent messages. All of this work should be done in the end of elaboration phase so that we know that the UVM component tree has been built and connected before we do this. All right, now we're going to look at an example of Python UVM with a simple DUT. Our DUT is the tiny ALU, and we have two ways to run the test bench. The test bench is the same. It's this Python environment here that uses a proxy that it gets out of the config.db, but that can be a Python proxy or it can be a CocoaDB proxy. The Python proxy works with only Python, and you can write the test bench in Python, and the CocoaDB proxy works with the simulator. Here's how that happens, as you have these proxies. The Python proxy is a UVM component, and the CocoaDB proxy is just a class, just an object. Both of them put themselves into the config.db under a label that you give them, and that label is proxy. The CocoaDB proxy also instantiates a couple of queues, one queue for receiving commands from the send-opt operation, and another two queues for delivering data from the monitors. These queues, the blue one here, are infinite sized, and when you do, say, command proxy get command, it does a get from this queue. So here we see the monitor UVM component. We're not going to look at all the components in the test bench, but this is a good example. It's a UVM component. It has a name and a parent, just like the UVM other components. So we call super init name and parent. One thing about CocoaDB is that you don't need to have an init method if you don't have anything to do in it. So it's not like system verilog where you have to have a constructor, even when you extend something that has a constructor. Now what we've done here is we have the monitor class right there, and when we instantiate it, we pass it the name of the function that we're going to call. It puts that into the method name, and then down here in the run phase, it loops for as long as we're in the run phase, and then it uses this get attribute command on the proxy to say, give me the function with this name. And if there is no function with that name, you get an attribute error and it goes up the stack and the program stops. But if there is, then a get method holds a handle to a function. We call that function to get the datum, and then we put the datum into the analysis port. So this is an example how introspection in Python makes it easier to write reusable code. So the get result is a different command. So that other one was get command. This is get result. They both work the same way. They return the result from a queue where the BFM is putting the data when it gets it. And here's the BFM for get result. It is this async tells you that this is a coroutine, which are functions that sit in an event loop and trade off time with each other, sort of like add pos edge kind of a thing. And what we have here is a function that's not a coroutine. It's an actual function called get result, but it's going to do a get on this queue that is fed by the coroutine, and it's going to block until there's data there. The BFM itself starts up, sets previous done to true, and then loops in a forever loop. It waits the falling edge of the clock. This falling edge is another coroutine that came from CocoaDB, and this DUT got passed to the proxy when it was created, if you remember, and so that's where we're getting that DUT. We say await falling edge of the DUT of the clock, and then we try getting done. Now sometimes done returns a z. If it returns a z, trying to turn it into an integer will fail with a value error, so we catch the value error and set done to 0. If done is 1 and the previous version value of done was 0, then we know we're at the rising edge of done, and we take the result data from the DUT and put it into the result monitor queue, which then returns the data through this call right here. There is no such thing as a cover group in Python. One has to figure out how to create functional coverage, and that might be other projects for the future or other aspects of projects. What I've done here is I've used a set, which is a data structure in Python. And this is a UVM subscriber, and like every UVM subscriber, it has a write function. So I receive the command from the command monitor, and I add it to the coverage set. And then in the check phase, when we're done with the run phase, I take the set of all ops, I subtract the set of the ops that I've seen, and if the length of that set is greater than 0, then I print out the list of operations that were missed. The sequence item is the same as the UVM sequence item. The difference here is that convert to string in UVM just becomes this magic method. This is called a magic method with these underscores called string, str. And that will, the print command, for example, will call string to get the string version of any object. So you can say print this sequence item and it'll call string, just like convert to string does. Equal is the equivalent of compare, except you can use the double equal sign to do the comparison between two objects. And it will call this method and figure out if the two objects are the same. Here's a test, the ALU test. This is the base test. We're going to have a CocoaTB version of the test that extends this and a Python version. But the base test builds the environment. It sets the logging level to debug. And then we saw this before, it raises the objection, gets the sequencer, creates a sequence, starts the sequence, and then after the sequence is done, waits for a second to let the last transaction finish and does a drop objection, which now you know will go and let all of the FIFOs shut down. The Python ALU test extends ALU test. It creates a Python proxy, and it creates a Python proxy. It is a UVM component, so we give it a name, we give it a handle to ourself, and we give it a label that's going to go into the config.db proxy. And then we call super.build phase to get the build phase from above. The CocoaTB ALU test mostly just leverages everything in the ALU test, except it adds a final phase. The proxy contains an event, which is like a system Verilog event, called done. And so what we do is we get a handle of the proxy, and we call set on done, and that tells the CocoaTB test bench that the pyuvm test bench is finished. Now, because we have this if name equal main thing here with this magic variable and this magic value, you can type Python tiny ALU UVM py, and it will call UVM root, getting the singleton of the root with run test, and pass it Python ALU test. That will launch Python ALU test, which will get the correct proxy, and you're off to the races. The CocoaTB test is a little more complicated. It is also a coroutine. It has a decorator at the top that tells CocoaTB that this is a test. So when we run with CocoaTB, it owns the test. It's the test runner. We are running the clock in our test, and then we create a CocoaTB proxy and put it into the proxy variable, and then also it gets stored in the config.db under the word proxy so that the pyuvm side of the test bench will grab it. We use the proxy to launch the BFMs, which are also coroutines, and this forks off these coroutines so they run on their own now. And then we wait for the falling edge of the clock just to give them a chance to get going. And then we create a thread that launches a run test in the UVM and passes it this CocoaTB ALU test name, which causes the UVM to create a CocoaTB ALU test and run. We start the thread, and then we wait on the proxy's done event, waiting for set to get called in pyuvm, and then we wait for a clock, and we're done. The test is finished. And the result is you run make sim in CocoaTB, and you get CocoaTB running. In this case, it's running on Icarus on my Mac, and you get out what you expect. The tests are passing, and the thing is working. So next steps are that you would do pip install pyuvm, and that will install pyuvm on your Python installation. You can come see all the code on GitHub. It's an open source project. It's still in the phase of getting the infrastructure in place, but the code's there, and see how this was implemented on GitHub. And now I'm ready for any question.